So if you're watching this video, you're either extremely stressed out right now because you're reviewing for the exam, in which case I have to say, take a deep breath, calm yourself, don't panic, okay? Or you're extremely bored right now because you're on a series of videos and it's been a bit boring just watching linked lists and you want to get to sleep. In which case, feel free to go sleep and come back to this one later. But this one is, notice that this is from my practice exam, right? This is a question that typically comes in my up in my practice exam and in my actual exams. So I probably won't go over this question when I go over the practice exam since I'm now making the video right here for it. But it says a list can be implemented in a number of ways. Compare and contrast an array list and a linked list. In which situations would you use one to implement a list over another? Right? Why would you use an array list or a linked list over a linked list or array list? Right? We want to compare and contrast these guys. Okay? So, I will be doing my write-up here in LaTeX, which may be a bit esoteric, but it should be fine for you guys to follow along. Okay. So, let's zoom in a bit. Alright. In general, so let's go ahead. So, basically, there's essentially three ways there's three ways we can compare and contrast the array list to the linked list. The first is how they perform their add and remove tasks. How well do they add and remove items? The second way we can compare and contrast them is by asking ourselves, how effectively can they do the get and set operations, right? How quickly can they go into the middle of an array and retrieve, of the list and retrieve data from that list? And then memory usage. How well do they use memory? Which is something we haven't really discussed too much about this. So zoom through there. Switch this to answers, right? There's nothing on here except practice answers, so, you know. Right. So now when I run this and compile this, we'll be able to get a nice chart as we go through. So I've already, I already went through and wrote this up, right? So comparing and contrast an array list to a linked list. So adding and removing. In general, it takes O of n to add or remove something in an array list, right? This is always the case because this is always the case if you add something in the middle, in the front of the list or into the middle of a size n list. If you're adding to the front, you have to shift n of these items out of the way so you can insert this last item. On the other hand, if you're inserting in the middle, you have to shift n over 2 items, which is still half the items in the list, right? The exception, as I mentioned here, the very last exception, is that if we're adding something to the end of the list, okay, which is constant time because you don't have to shift anything over, right? Now the exception to the exception, of course, is what makes it fun, because if we add in the last item and the list is full, then with the array list, we need to reallocate the list, which means we make a new list that's twice as big as the original list, and then take the first item, move it on, take the second item, third item, and so on. So we copy over all n items, which takes O of n time, and then we can finally add the last item in at constant time, right? So it takes O of n time, right? So it takes, in general, it's O of n, except when it's constant, except when it's O of n, right? But once you know those three cases for array list, it's fine. And with remove, on the other hand, right? Notice I only talked about add over here. Let's not forget about remove, since it's supposed about add or remove. For remove, it's O of n if you're removing something from the front or the middle, but if you're removing from the end, it's always constant time. You don't have to worry about reallocating. Now, you can make the argument over a lot of different if you're adding to the end a whole lot, then it's constant time amortized, because we're going to be reallocating a whole bunch. Sorry, we're going to be reallocating, but it's not going to occur actually a whole bunch. Right? Every time we reallocate, it's going to be twice as long between, we'll have to wait basically n more times before we reallocate again, right? N more additions before we reallocate again, right? Because the initial size, remember, a list is 10, then it goes up to, the initial capacity of a list is 10, then it goes up to 20, then it goes up to 40, then it goes up to 80, it keeps doubling. Okay. So remember that when we get down to here. For a linked list, if we're adding to a location we have a reference to, such as the head or the tail, then it will take constant time. But in all other cases, unless you have a reference to it, we have to actually search for that actual node, which takes linear amount of time, right? We have to use the getNode function. We have to actually manually search for that node. We can't for that node or for that index, right? We can't actually jump to a specific index in a linked list. We have to manually start at the beginning and walk through it. In an array list, since they're built off arrays, you can just kind of teleport to it. So linked lists, obviously. So which one's better? It depends on your use case. If we're just adding things to the end, array lists are perfectly fine. If we're adding things to the beginning and end, linked lists will almost always run faster, though, because you never have to reallocate for this, right? However, if you're always adding into the middle, it doesn't really matter what your use case is, because these both are terrible equally at inserting into the middle. What about get and set? Well, that's where it becomes very interesting, right? So let's go to here and actually write that up, right? Array lists take O of one time, constant time, to get the value at a specific index or change the value at an index as it takes advantage or as that is how long it takes using the underlying array, right? What about a linked list? A linked list, on the other hand, you have to linked lists. Linked lists. So take. Whoops, wrong one. O of one time to get or set a value as we have to find the specific node at that index. Right? We have to start the first node, then go to the second, go to the third, fourth, so on and so forth until we get to the right index, until we get to the one we want to actually retrieve or change. Okay, so now what about, and let's go ahead and put that into a readable format. Okay, what about the memory usage? Right, memory usage. Okay, so we haven't really spoken about this, but let's talk about how much memory these guys use, because these guys have an overhead cost of memory, right? An array list, for one, it allocates this big chunk of memory, right? Right, and it allocates an array of whatever the size you need. And as we add items, what's going to go on? We need to, once the array fills up, we have to reallocate and make a new array twice the size. Now so imagine what would happen if we get unlucky. Say we've got something we're dealing with an array of capacity 1 million, right? We add our million in first item, okay? What happens? Well, we've just filled up our capacity of 1 million, so we have to reallocate and make a size 2 million array, okay? And we add that 1 million first item, and we never add we never add another item to it. Okay, so that means we have 999,999 empty slots just waiting there, just hanging out there because we added something, it reallocated, and we never used anything beyond that last thing we reallocated for. So we've got all these wasted 32-bit slots, which would hold the memory we would have wanted to hold the memory location of some actual data, but can't here. So here, array lists, I would say one of the issues, array lists can double. And you will have to go into a bit more detail here, right? Array lists double their size. which means ... all those things I just said. And what about over here for a linked list? How do those use memory, right? We always create one node, right? We're just going to create one node every single time we... this isn't real, right? It doesn't do anything. We aren't going to waste any memory. We just create a node, right? Each time we need to make an item, right? We don't make more nodes than we need. Well, there's a cost to using nodes. There's a cost. Specifically, we have this cost over here. The cost to not actually hold the item, but we spend 32 bits holding the memory location of the item. Now, this isn't necessarily a fair comparison. Now, this, we can't say that this is any more expensive than ArrayList. It's a fair comparison, but it's not any more than ArrayList, because in ArrayList, each slot also holds the memory location of an item. So this is the same cost over here that we would have as an ArrayList. But every node for a singly linked list, we spend an extra 32 bits per an item to hold the memory location of the next item, or the next node, which would hold the memory location of the next item. And then in a doubly linked list, we spend 64 bits to hold both the location of the next node, which would have the location of the next item, and also the location of the previous node, which would have the location of the previous item, right? So we've got this, essentially this overhead here for storing these items. Now, this might actually pale in comparison to the memory that's used up by the actual item themselves, but there's an overhead cost here, right? These use up extra memory. So it turns out actually array lists are a bit more space efficient if and only if we don't have any empty slots. Otherwise, the linked list might be more space efficient. It really depends on the case. It depends on whether or not the capacity of the array list has been filled up.